Hello and welcome to another episode of How to Understand X. Today we're going to be talking about matrices. This is a weird topic to kind of try and make a video about because matrices are just a different system of numbers. It's just a different way to arrange numbers and to, perform basic operations with them. And trying to make a video about all of the intricacies of matrices and, however long this video is going to be, that's not really possible. It's kind of like trying to make a video on the letters of the alphabet. Like, sure, I can tell you what the letters are. I can tell you that you can combine letters to make certain words, but I can't really teach you all of English in, 2 hours or something. So I'm not going to try. I'm just going to tell you what a matrix is, some of the basic operations that happen on matrices, and some of the connections that we can make with matrices and, the larger world of mathematics in general. So what is a matrix? Let's write that down. A matrix is just a rectangular array of numbers. For our purposes, these are going to be real numbers. Rectangular array of numbers. We'll call these real numbers. And that's essentially it. These matrices, I think it's kind of like sets, and then once you actually say what a set or a matrix is, it kind of loses its mystique a little bit. A matrix is not particularly difficult to see, but it's interesting. So let's draw, or at least write, a representation of a matrix. We say that a matrix is M by N if it has M number of rows and N number of columns. So a 2 by 3 matrix has 2 rows and then 3 columns. So let's draw a real quick matrix. It'll be, say, 1, 2, 3, 4, 5, 6. Oops. 5, 6. So that's going to be 1, 2 rows, and then 1, 2, 3 columns. So 2 by 3, M by N. And yeah, we're going to be referring to each element, or each thing. Element is just a number in matrix. We'll be referring to each element by their location relative to these columns and rows. So if you have a matrix, big A, this tends to be bolded, big A, and you have, say, n by n number of columns, n by n rows and columns, so we have, say, 1, 2, 3, dot, 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 m, and then we have 1, 2, 3, dot, 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 n, number of columns, then A1, 1, and A2, 2, and then, not A2, 2, that's not A2, 2, this is going to be A1, 2, so 1 is M, so first is the row, and then the second is the column, so 2, and then the one directly right of that's going to be A1, 3, and then on, and then it goes down 1, so the number of rows, or the row number, is going to increase, and you'll have A2, 1, A2, 2, A2, 3, and on. Then you have A3, 1, A3, 2, A3, 3, and on. But this number, it's not 11, it's not 12, it's just 1, 1, as in number of rows and number of columns. So the element at A1, 1 we'll refer to as this 1, 1, and this 1, 2. We'll be calling them IJ. Again, this is just the same. This is the row number it's at and the column number it's at. I is the row number and J is the column number that it's at. And yeah, I mean, that's pretty much it regarding what a matrix looks like. As to what a matrix represents, for us, we're going to keep it strictly in linear algebra. That includes vectors, so it's not, just basic addition. We will talk about some interesting stuff today, but we are going to be we are only going to be talking about linear algebra for right now. And the way that matrices are defined as Aij elements in some matrix A, no, in A with I rows and J columns. The way that this is defined allows us to actually do operations with different matrices. We can define addition, subtraction, multiplication, transposition, inverses. We can do quite a bit with matrices because they're just assemblies of numbers, like the operations that matrices can do are only possible because they are just part of the number system. So, yeah, we can do some interesting math with matrices. And so, yeah, let's get into some terminology. We have, where should we start? Let's talk about some important terms. So, we have the row vector. This is a 1 by n matrix. So it will have exactly one row and n columns. So to kind of draw what this would look like, it could be 1, 2, 3, 4, on and on until you get to n. And there's only one row, so there's no numbers down here. Not 0, but there's nothing going down. So this is a one row matrix, and this term vector is an important one. We will talk about vectors shortly, but just keep that somewhere. And we can also say that a column vector is a n by 1 matrix. So this will be n number of rows in one column. When we are doing some vector stuff today, we are probably going to be using only these column vectors, but just as a representation, this could go 1, 2, 3, 4, on and on and on until you get to n. So 1, 2, 3, 4, and there's only one column, so n by 1. And yeah, both of these can be used to represent vectors, but for today we're only going to be using column vectors when we are trying to draw and do math with vectors. And let's also talk about a square matrix. I think it's relatively intuitive what this is going to look like. It's going to look like a square. Square matrix is just a matrix of a size n by n. And we actually say that this square matrix, it's not if, it will be n by n or 1 by 1. When we have a square matrix of n by n size, we can say this is of order n. Order n. So yeah, let's just very briefly draw something. We'll have 1, 2, 3, 1, 2, 3, 1, 2, 3. There are 3 rows, 3 columns, n by n, and this is a square matrix of order 3. So, yeah, square matrices are particularly important because we do have to do some somewhat odd stuff for when we talk about multiplication. But let's go back to what we described was our vectors. Vectors, I mean, I know that this is a matrix video, but vectors and matrices have a lot to do with one another. if you have like a Venn diagram of the operations that we can do with vectors and the operations that we can do with matrices, it's going to have quite a bit of overlap. So let's define what a vector is. There are two main definitions of a vector. One connects back to matrices. It's just a mathematical object with, well, let's actually talk about the first definition of a vector. It's going to be a mathematical object with magnitude and direction. You will most likely see them written as kind of like a line segment. You'd have this and an arrow. This will be the head of the vector. This will be the tail of the vector. And this is the direction that it's facing, going up and to the right. That's not the correct way to say it, but the direction is in that way. And then the magnitude is going to be the length of the line segment. And so this is probably the most common definition of a vector, mathematical object with magnitude and direction. And we can actually write our column and row vectors as vectors. So, one second. And I also forgot to say the quote-unquote second definition of a vector. This will be mostly used in computer science. This is actually rather similar to the matrix definition. It's just a rectangular array, for vectors that only have one row or one column, this will be a just list of numbers. We will be working with both of these, but this is probably going to be, since we're doing matrices, this will also be relatively important, but for right now, that first definition, the mathematical object with magnitude and direction, is going to be what we're going to be working with. So let's try and represent a column vector as a vector. We're going to be working with polar vectors. Not polar, Cartesian vectors, right? Cartesian's with the x, y, but polars with the, let's just draw a polar really quick. I think it would look something like this, where you have, this is your vector, right? This is the magnitude, the length of this. Instead of defining it by where the head is, which is how we would do it in Cartesian, we have to define it by this angle from the x-axis. So this could be like 45 maybe. It doesn't quite bisect it. We'll say 45. It doesn't matter. This will be a written as 45 degrees and then like 17 or something. I'm not sure if you use parentheses for polar vectors, but we're going to be talking mostly about Cartesian vectors. It'll still have a magnitude and direction, but the direction is going to be defined, the magnitude and the direction are both going to be defined by the point on the xy axis. So if we have this point x and then this y value y, and we draw a point at xy, we will be going from the origin to xy, and that's the vector at xy. So let's look at a very basic column vector. We're going to have a 2 by 1, and it'll be 1, 2. We can also have 3 by 1s and 4 by 1s, but we'll actually do a 3 by 1, but right now we do not need to talk about 4 by 1 and 5 by 1. Very quickly you'll realize that we will have to go into 4D space and quaternions and then 5D space. I'm not gonna lie to you, I don't know what 5D would even look like, but I do know kind of what 4D representations of physical objects are supposed to look like, and if I can barely draw 3 by 1, I will not be able to draw 4 by 1. So how can this 2 by 1 matrix be represented as a vector? Well, we can say that this 1 corresponds to an x value, and this 2 corresponds to a y value. And then this 1 for this 3 by 1 is going to correspond to an x, this 2 will correspond to a y, and then this 3 will correspond to a z. So obviously now we have dimensions. We have an x and y plane, and then we have an x, y, z plane. So this will be 3D, and this will be 2D. So I guess if you have an n by 1 or 1 by n vector, the size of n is going to be the dimensions that are necessary to actually visually represent it. So let's draw really quickly a 1, 2. We have a xy plane, right? We only have two rows. So we have a x of 1 and then a y of 2. And so let's draw the head of our vector right there, and then we just draw a somewhat odd-looking straight line from the origin to the head, and that will be a magnitude. Now, well, not a magnitude, that would be a vector. We can actually calculate magnitude right now, and it's not too hard. We just need to do distance formula. We have 2 points right here, 1, 2, so we can do the square root of x2 minus x1, not x squared, don't know why I wrote that. And we have, well, we can actually kind of prove this really quickly. This is just another application of Pythagorean theorem. If you have a point x1, y1, and then a point x2, y2, x2, y2, if you drop a altitude from that point to that point, and this will be, you know, x1, y2, and you just try and find the hypotenuse, you just do the distance from here to here. Since the xy's are, well, the x's are the same, we can have this distance just be x2 minus x1, and then this distance between the y's, y1 and y2, is going to be y1 or y2 minus y1, and then this distance squared is equal to this distance squared plus this distance squared. That's just a Pythagorean's theorem, you know, c squared equals a squared plus b squared, and then we simply square root to find the actual distance. And we'll do something rather similar in just a second to try and find the distance for this one. But yeah, that's just another application of Pythagorean's theorem. So let's calculate the magnitude of this vector. We're going to have square root of 1 minus 0, so 1 squared, plus 2 minus 0, so 2 squared. And so that's going to be 1 plus 4, so square root of 5. And most vectors that are going from the, not most vectors, all vectors that leave the x-axis, or not the x-axis, the origin to the head of the vector, you only need to calculate the x values squared for those ones. So we'll try to represent, well, actually, let me say something really quick. I've been jumping a little bit. We have to talk about I and j. This is not the I and j of, well, actually you could think of it as the I and j of matrices, but, wait, no. This has nothing to do with the I and j of matrices. Let's draw I and j. Well, I and j, it's pretty simple. It's just another way to represent a vector. It's going to be, I is the unit in the, like, x direction, and then j is the unit vector in the y direction. So each vector has to go over a certain number of i's and then a number of j's up. And, you know, vectors obviously are a lot more complex than I'm making them seem right now. There's just so much more to talk about with vectors that I don't really think I have the time to talk about right now. I might be able to do a video on vectors at a certain point, but vectors are definitely very distinct. Even though that interlap between matrices and vectors is rather large, there is just so much more to talk about in vectors and in matrices that this video will not be able to cover. But yeah, let's look back at this 1, 2. So if this is one unit in the x direction, one vector, one unit vector, and this is one unit vector in the y direction, then we have to have another unit vector, so another j, and that I is still going to be I. So once we get to 1, 2, the amount of vectors that have been, you know, done is I plus j, so I plus 2. j. So yeah, this is just, there are three representations that we have right now. We have this Cartesian point, so 1, 2, number of x units needed to be traveled, number of y units that need to be traveled. We have this matrix, 1, 2, or column, row 1 corresponds to the x, and then row 2 corresponds to the y, and then we have I plus 2j, which is the number of unit vectors that we have to travel in the x direction plus the number of unit vectors that we had to travel in the y direction. So yeah, those are just representations of matrices, of vectors that we might need to use at a certain point. But let's talk about these 3x1s. I promise all of this will have some application at some point. I will, do some actual math with these, but let's draw an xy. Once we have this z corresponding to depth, we do have to give it another dimension. So let's try and draw this 1, 2, 3. We'd have x go somewhere around there, and then we have 1, 2, and then we have 1, 2, 3. These are going to be just tick marks, and so when we draw, I kind of try to think of like a rectangular prism that goes from the x-axis to the y-axis, and then from the x-axis to the z-axis, and then from the y to z. So let's kind of draw that. Okay, that's not too awful. Okay, spoke too soon, that's not great. But if that's the point x, y, z, or 1, 2, 3, and you just draw a diagonal from the x, y, z to the origin, that's going to be a vector. And the magnitude of this is how you calculate distance for the 2x1, and that's going to be x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And for a relatively normal proof, again, this is just going to be another representation of distance formula. So if you can see that this diagonal from the origin to the endpoint of that prism is just the composite of these two rectangles, I can't really draw it correctly, but let's draw this. If you can see that this diagonal between the two is just the composite of two triangles, then you can kind of see how distance formula can be used to sum up the distance between those two triangles to get this formula, but I will put a much nicer looking visual representation of this idea in the comments, not in the comments, in the description. So yeah, let's do this magnitude of this vector. So it's going to be square root of 1 squared plus 2 squared plus 3 squared. So 1 minus 0 squared plus 2 minus 0 squared plus 3 minus 0 squared. And this is going to be equal to 1 plus 4 plus 9, so 14. Not whatever that's supposed to be. But yeah, this will be square root of 14. And this is just the magnitude of this 1, 2, 3 vector. And the idea of addition is, we're going to actually go back to our I and j notation real quick. The idea of addition in vectors is somewhat interesting. So we have I units and then j. And if we say this is 1, 2, right? And this is I plus 2j. Then if we add another unit, if we had a 2I plus 2j, then this is one vector, and then this is another vector, right? The vector from the origin to 1, 2, and the vector from the origin to 2, 2. And this, well, let's look at our matrix representation of I plus 2j. We said this is 1 and 2. And this one, since we have 2 unit vectors in the x direction and 2 unit vectors in the j direction, the y direction, we're going to have 2, 2. So the y has not changed, but the x has. So if we try and subtract this from this, we're going to get I. We had to add I plus 2j plus I And I, if we try to represent that, it doesn't have a j, so it only goes 1, 0, no change in the actual unit vector in the y direction. We have 1, 2 plus 1, 0 equals 2, 2. And let's even draw a representation of a slightly more different vector. We have, say, 2, 3. And then let's say we have like 6, 5. Let's draw this vector, and then let's draw this vector. What's the addition between these two? Well, we have 2 units traveled in the x direction, and then 3 units traveled in the y direction. And then for this vector, from this is 5, 6, this is 2, 3, we have 6 units traveled in the x direction, so 6i, and then 5 units traveled in the j direction. So this will be the matrix 2, 3, if x corresponds to I, and then y corresponds to j. And then this will be 6, 5, right? And if we did, well, we're going to be actually subtracting, but if we try and add something to this to get to this, well, 6i minus 2i is 4i, and then 5j minus 3j is 2j. So this is 4, 2. And that's just another representation of matrix addition through vectors. This is obviously, very basic vectors, but this definition of addition between these two vectors actually translates all the way to addition of matrices. And that is as follows, given some matrix big A. One second. So given some, let's say, matrix A equals all of the elements A, I, J, and B equals all of the elements of B, I, J, then A plus B is equal to all the elements of A, I, J plus B, I, J, or, well, let's actually say that if we have some addition A plus B equals C of some matrix of the sum of these two matrices, then if all of these elements are C, I, J, that was the weirdest I think I've ever written, C, I, J, then every element C, I, J is equal to A, I, J plus B, I, J. And, yeah, I mean, that kind of makes sense. This might be a little bit too complicated, but let's just say we have a matrix 1, 2. This works with vectors, so it has to work with matrices because both of these are mathematical objects and just arrays of numbers. So if 1, 2 plus 2, 3, those two vectors, we have, this would be 1i and then 2j, and then this is 2i and 3j. When we add those together, we get 3i and 5j. And then when we when we put them back into our matrix format, we're going to have 3 and 5. So we did an addition. We have A11 and A21, and we have B11 and B21. So those A11s, we add them together, and then those B 2 ones, those B 2 ones we add together. Or, I got that incorrect. We have A11 and B11 that we have to add together, and the A21 and the B21 that we have to add together. So this matrix addition, I think there is a way to add matrices of different sides, but for right now, matrix addition is going to be only of 2 matrices with same size. And same size is just same n by n. So, yeah, I mean, I think that's relatively intuitive. We saw how that works with vectors. So if vectors are just representations of certain types of matrices, then it just makes sense to have this like definition extend to matrices as well. And then let's talk about, you know, some other things. Well, let's really quickly go over subtraction. We actually did a little bit of subtraction just a second ago. We did a minus b equals c, then all the elements of cij is going to be equal to aij minus bij. And we actually have to do subtraction to get to understand how matrices and vectors are connected. Like when we had that 2, 3 plus something is equal to 6, 5, we had to convert to I and j format, so 2i and 3j, and 6i and 5j, and we actually had to subtract our i's and then our j's to see 4i and 2j, or this matrix 4, 2, to kind of see that this like expression is equal to 6, 5 minus 4, 2. That makes sense. This is A 1, 1, this is B 1, 1, this is A 2, 1, this is B 2, 1. So these are two matrices with the same size. These are actually column vectors, but column vectors are obviously matrices as well. And we had to do A 1, 1 minus B 1, 1 and A 2, 1 minus B 2, 1 to get this. So, you know, if matrix subtraction can be defined for a certain type of matrix, then that's how you just kind of say it works for all matrices. And that might seem like a kind of cop-out way to say that this works, but quite a few proofs actually kind of work by that same logic. Like the proof of why like irrational numbers to the power of irrational numbers are rational is kind of a funny one, because I mean I could do it really quickly. It's not a super complex proof or anything, but if the like exponent of a irrational number is irrational, then the final answer is rational. That idea needs to be proved in two ways. You get two irrational numbers. We'll work with root 2 and root 2. If this power is rational, then good. We don't need to do anything else. But if this is irrational, then if we did this to the power of another irrational, which is going to be root 2, also irrational, then these root 2 and root 2 by, exponent properties, when you have a power to a power, you multiply, you get root 2 to the power of 2, which is going to be 2, which is rational. So both cases work, which means that an irrational number to the power of an irrational number can be rational because one of such like example exists. And it's hard to generalize this for all irrationals. It's kind of like, you kind of just say maybe this could work for everything, but really it's just that it's like if you can prove that this happens with column vectors, then this can happen with all kinds of matrices, which we've proved that it does work with column vectors. That's how you add the two and how you subtract the two. So let's do like a very brief example of what this might look like with non-column vectors or row vectors. Some just regular old matrices will have, say, a 2 by 3. God, that's one of the worst brackets I think I've ever written. We have a 2 by 3 matrix going from, say, oh, this is going to be 3 by 2. Excuse me. So let's come up with some numbers. We'll say maybe 4, 9, 7, so 3 rows. So m is equal to 3, and then n is equal to 2. We'll have 5, 2, and then 1. And this we're going to add to another 3 by 2. that being 1, 17, 11, 12, 4, 3. I know, I'm really good at coming up with random numbers. We have n equals 2, and then m equals 3, and this is a11, this is b11, so we add those together. We have, running a little bit out of space, we have a11 plus b11, so we can even write that out, 4 plus 1, and then we have a11, I mean a2, no, a12, and then b12, so 5 plus 17, and then we have a21 and a22, so we have b21 and b22, and then we get 9 plus 11 and 2 plus 12 for a plus b 22, and then we have a31, b31, 7 plus 4, and a32 and b32, so 1 plus 3. And yeah, that's relatively normal looking. We'll get, at the end, I'll kind of have to write this a little bit small. We have 5, 22, 20, 14, and then 11 and 4. So yeah, matrix addition really isn't as difficult as it might appear to be, but these are only of the same size. I think there's like a certain type of sum of different size matrices that's like some crazy calculation, but let's get into something I think a little bit more interesting, and that is scalar multiplication. Let's first talk about what a scalar is, and for this we're going to have to go back to our vector ideas. We have a scalar is somewhat like a vector. It is a mathematical object, but this scalar only has magnitude. With only magnitude, no direction. So this is obviously not going to be very easy to graphically demonstrate because there's no direction. There's no head because there's only magnitude or length of some line segment. So we actually can't really describe, or well, we can describe what it is, but we can't really show what it looks like without having a pre-existing pre-existing vector. So let's have one. We have our original example. We have a 2x1 matrix, which we will again talk about how scalar multiplication connects from vectors to matrices. We have a 2x1 matrix of 1 and 2. 1 corresponds to x, and then 2 corresponds to y. So let's draw that out one more time. We have 1, 2. Well, let's put 1, and this is 2. X, y. And how do we kind of show a vector? Well, how do we show a scalar with our original vector? Well, a scalar only has magnitude. It does not have any direction. So if we multiply a scalar to a vector, we should just be increasing the magnitude of the original vector, right? It doesn't impact the direction in any way. Because if it was, like that, and this was a different vector, let me try and organize my thoughts in as lucid of a way as possible. If we were to multiply two vectors, they will go in different directions because these are not the same, right? But if we multiply a scalar to an existing vector, we simply increase the magnitude. So let's draw that really quick. If we multiplied this by a scalar, we're just extending the magnitude. Let's say that this is 3, 6, because we had to travel 1, 2, and then 1, 2 up, so this is going to be, well, we have I and 2j, so I plus 2j is going to be the representation of that vector, and then this is going to be 3I plus 6j, and we had to do 1 times 3 to get 3I, and then we had to get 2 times 3 to do 6j, so we actually had to do 3I plus 2j, and if we go back to our original matrix way of representing that, we have 3 times 1, 2 is equal to 3, 6. And that 3, that first one, this is a scalar. It's just a mathematical object that scales this 1, 2 by a factor of 3, or vertically stretches it because we are doing a linear, because it's a line, we're doing a linear transformation. This 3 is simply scaling this matrix and this vector by a factor of 3. So, yeah, I mean, that's pretty cool, in my opinion. So, yeah, I'm not sure if I'm fully illustrating what's happening as well as I should, but this scalar multiplication, if you have a vector or a matrix and you give it a scalar, you give it a mathematical object with only magnitude, no direction, then you are not affecting the actual vector values. It'll always be in the same multiples of I and j. In this case it was multiples of 1 for I and multiples of 2 for j, but every scalar simply scales those i's and j's. They do not change the values. This cannot be like 3 plus 5j or 2 plus 6j, because you are scaling it by a factor of 3. So scalar multiplication is for matrices going to be the same way as it is for vectors, because, again, vectors can be represented as matrices. We're going to have scalar multiplication be defined as this. Well, this is only going to be one of the types of multiplication for vectors. We have if big A is all of the elements in A that follow A, I, J, and K, A is some type of a scalar times this matrix, then this is all the elements of K, A, I, J as well. This is the product of K and A, so this is the product of K times every individual element of I, J. So let's go back to our 3, 1, 2. This is A1, 1, and this is A2, 1. So we have 3 times A1, 1s, or K times A, I, J, and we're going to have 3, and then we're also going to have 2, or A2, 1 times 3, so K times A2, 1, which is going to be 6. So yeah, we're just scaling this column vector by not a column vector, it is just a vector, but we're scaling this vector by a factor of 3. We are not changing the direction that this vector is traveling, just the magnitude that this direction... Okay, I don't know what's up with me today. I can speak English, I promise, but we are scaling this vector by a factor of 3. We are not affecting the direction that this vector is traveling in any way. We are simply affecting the magnitude of this vector. And so, yeah, I hope that's kind of a good representation of what a scalar is and what it looks like. We will be doing quite a bit of scalar multiplication, or, well, you will probably be doing a lot of scalar multiplication once you get into matrices further and further. But, let me actually... And, you might be thinking about division. Like, we have defined addition, subtraction, and multiplication of matrices, but we haven't defined division yet, because we can't. But before I get into what we can do with matrices, instead of division, I do need to define a couple of things. We have the main diagonal. The main diagonal of a square matrix is just all of the elements where I is equal to j of some big A equals ij. Not A times ij. A subscript ij. There we go. If A is all of the elements that fit Aij, then the main diagonal is where I equals j. So let's draw a matrix real quick. This is almost always going to be a square matrix. We have a No, I don't know why I said almost always. It is always going to be a square matrix. We have A11, A12, A13, A21, A22, A23, A31, A32, and then A33. Where does I equal J? 1 equals 1, 2 equals 2, and 3 equals 3. This is the main diagonal of big A. And this is just the top left corner to the bottom right corner. And that's probably the best way to remember this. This might seem kind of useless, and it's not like entirely useless or anything. There are quite a few proofs that require the main diagonal, I think. Don't quote me on this. I think there's a way to represent the like set of rational numbers and why that's like you can represent a set of rational numbers as a matrix, and then if you just eliminate the like main diagonal and do like a big swooshing line, like okay, I'll just try and draw what I'm saying. Like if you have this 1/2, 1/3, 1/4, and on, and then you have we have this will be a infinite matrix, right? This will go 1 to infinity, but 1, 2, 3, 4, 5, and you can still count those 1, 2, 3, 4, 5, 6, and then if you have 2 over 1, 2, and then 2 over 2, we're going to write that as 1, but actually, you know what, just for the sake of, consistency, let me write these as their actual rational. So if you define the set of rational numbers as like a matrix of, m by n rows, I actually need to kind of say this correctly. You have m by n rows, and each element at aij is just I over j, or m over n, but then we have 1 over 1, and then 1 over 2, and then 1 over 3, and 1 over 4, and on, and then we'll have 2 over 1, 2 over 2, 2 over 3, 2 over 4, and on and on. Then we'll have, uh, 3 over 1. Actually, I'm not sure if this uses the main diagonal, but 3 over 1, 3 over 2, and then 3 over 3. If you just count every single term in this kind of like a swooshing pattern, and you just eliminate the main diagonal, you should be able to count every single one. It would obviously take you an infinite amount of time, but since you were able to count every single element in this set of rational numbers, or in this matrix of rational numbers, then this set of rational numbers, Q, is countable. So this has this this cardinality of Q. It's like Aleph null. I don't know how to. Well, I know how to draw Aleph, but it's not great. Let me try and look at it one more time. We have a like this kind of thing, and then it goes like that, and then it goes like that and that. So we have Aleph null, and that means that it's just a countable infinity. I'm way off topic here, but the main diagonal, while it might not be super useful, just all the elements aij in big A where I equals j, it can be useful, and it's also useful for defining our unit matrix. And so yeah, let's define our unit matrix. A unit matrix is just a matrix, a square matrix of order n, where the main diagonal is 1 and every other element is 0. So unit matrix. This might be also seen as the identity matrix, or I, but I prefer unit matrix. I don't really know. I might be flipping between the two at any given moment, but there we go. Unit matrix I, and this is going to be a matrix, a square matrix. So n by n, A, with um, main diagonal of 1s and a, so every aij where I does not equal j, aij will equal 0. So let's just draw a very quick one. We have 1, 1, 1, and then zeros for every other element. So yeah, this is A11, A22, A23, A33, and those are elements of big A where I equals j, so the main diagonal, and that will equal 1, and then every other element where I does not equal j will be 0. This will be a unit matrix or identity of order 3. Alright, and that might seem kind of useless, but it's actually kind of important in seeing the inverse of a matrix. We can't actually define division of matrices. Oops. Oh, wait. Before we actually talk about the application of the unit matrix or the identity matrix, we do need to talk about the multiplication of matrices that are not scalars and vectors. So let's do that. Because, if we're trying to define division as an operation, we do need to define multiplication, which is, of course, the inverse of division and vice versa. So, yeah, let's try and multiply two different matrices, or at the very least define what matrix multiplication looks like. So yeah, we define scalar multiplication, but matrix multiplication is slightly different. Scalar, again, is just a mathematical object with only magnitude. So if we multiply it to the rest of a matrix, if we kind of think of a matrix as just vectors, even though, not all matrices are vectors, even though all vectors are matrices, then we simply increase the magnitude of each individual element of some matrix A by a factor of k or something. But matrix multiplication is when you have two separate matrices. So let's define A as an m by n. So we're going to have a m number of rows. So let's have 1, A11, A12, and then, on and on and on until you get to A1n, A21, A22, on and on until you get to A2n, and then this will continue increasing on that main diagonal, so ANN, and then we're going to have, or not ANN, this will be MN, and then we'll have a 3, 1, it'll continue going across like that, and then we'll have actually, let me stop at A21, and we can go on and on, and we will get to AM1, and then this will go like that. Okay. And obviously this will increase across that, and this will increase across that, and that'll be A, any size matrix. And then B can be an IJ, right? We'll have a, not sure if I should go to IJ. Let's say that this is M by N, and let's go to N by P, making sure that these are the same, just for now. And we can say that this is the same kind, right? It'll be, B11, B12, often 2, B1P, and then this will be, B 2, 1, B, 2, 2, on and on. On that row, it'll go to A, 2, P, and then it'll continue increasing across the main diagonal, so B and P, and then we can say that this will go off into A and 1, not A and 1, B and 1, B and 2, and then, on and on. Let's just draw those ellipses. And then C, we want C to be a product, and we'll call C sum M by P. We'll call C sum M by P, and this will be the same kind. It'll be, start at C11, go to C12, on and on till you get to C1P, and you go C21, C22, C2P, and then you go off into CM1, and then CM2, off into CMP, as it continues across that main diagonal. Alright, and we will try and define A times B equals C. This matrix multiplication of all the elements of Cij, this will look like Cij is equal to AI1 plus, times B1j plus AI2 times B2j, and then on and on and on until you get to AIN times BNJ, right? And I wanted those to be the same, so that we can actually see this and J be the same. And then this is just going to be the sum from n equals 1 of every element AIK times BKJ. Alright, so let's try and write this out correctly. This is just matrix multiplication. Every element Cij is just going to be the term by term multiplication of the ith row of A and the jth column of B. And you just sum these products to get to that Aij. So, yeah, this is obviously not something that you have to remember, but you do need to see the pattern that matrix multiplication follows. So let's try and show an example. Let's say that we have I just searched up example. Let's say we have a 2 by 3, so 2 rows, 3 columns matrix as follows. It's not coulombs, it's columns. So columns, and we have a 1, 2, 3, 4, 5, 6, and then this is going to be multiplied by a 3 by 2. That is 7, 8, 9, 10, 11, and 12. Okay. And so, as I said, this needs to be the, multiplication of all of the elements in the ith row times all of the elements in the jth row for Cij. So, if we have j equals 1 for this one, this is the first column, and this is I equals 1, or the first row of A and B, then we have to do all of the terms in the ith row times all of the terms in the jth row. In the jth column. And then we have to add them up. So we have 1 and 2 and 3 times 7, 9, and 11. So we have to do 1 times 7, 2 times 9, and 3 times 11, or a 1j times b 1. I mean, wait, bj1. So we do 1 times 7 plus 2 times 9 plus 3 times 11. That'll be 7, 18, 33, 58. And that will be Cij. If I equals 1 and j equals 1, then C11 will be 58. So let's draw what we have. C11 is going to be 58. And we only have I equals 2. That's the largest value of I. And then the largest value of j is going to be equal to 2. So we can only do this for C11, C12, C21, and C22. So we're going to have a square matrix of order 2. Now, let's do the ith row again, I equals 1, and the jth column of 2. So we have 1, 2, 3 times 8, 10, 12. So we're going to have 1 times 8 plus 2 times 10 plus 3 times 12. So it's going to be 8 plus 20 plus 30. 8 plus 36 is 44, plus 20 is 64. So that will be C12, where I equals 1, j equals 2. And then let's do the ith column of 2 and the jth column of 1. So we're going to have 4, 5, 6 times 7, 9, 11. So we're going to have 4 times 7 plus 5 times 9 plus 6 times 11. So that's going to be 66 plus 45. What's 66 plus 45? 111 plus 28. Yep, 139. And then we have to do the ith column of 2 times the jth column of 2. So we're going to have to do 4, 5, and 6 times 8, 10, and 12. So running a little bit out of work right now. We have 4, put it over here. We have 4 times 8 plus 5 times 10, and then 6 times 12. So 72 plus 32 is 104 plus 50, and we have 154. So yeah, I hope you kind of see the process. This is called the dot product. Don't ask me why. I don't really know why it's called the dot product. I mean, there's... I was about to come up with something, but I can't really. So, yeah, let's go back to what we defined. Our original thing was this is the sum. I'll erase matrix is a rectangular array of numbers. I'm hoping that by this point we can kind of intuitively know that. We have Cij, so every element in C will be of the order Cij. This is equal to the sum k equals 1 to n of aik and bkj. So k has to start at 1 because you can't have the 0th element. They'll always start at 1. And you have every element in the ith row. So for this one it was I equals 1, and we had to multiply that to every element in the jth column, where k and k are the same value. And then this will be everything j equals 1. And you have to do that for every element in Cij. This might seem, tedious and annoying, and to be honest, it is kind of tedious and annoying, but it is important. You need to understand that this is how we do matrix multiplication. You have to multiply every term in the ith row with every term in the jth column of two matrices, and you just add them, all of them together. and that's called the dot product, and that will be the element corresponding to the same I and j values that you multiplied for. So yeah, I mean, I think it makes sense. There's also another important idea that we need to talk about, and that is multiplication is non-commutative. This is actually one of the, best examples of non-commutative multiplication. So if you have two matrices A and B, and AB is going to be the product of those two, AB does not equal BA. That's because when you flip those, when you have that B, I, K, and B, and then A, let's write down our subnotation again. Starts at K equals 1 to N, and you have B, I, K instead of A, I, K, and A, K, J instead of B, K, J. You're actually multiplying and summing completely different elements for, different sizes. Like, look back at this one. If we were multiplying B to A, if we're doing this times this, we're going to have to do a completely different process. We would have the ith row be 1, and then the jth column be 1, 4. So, there's obviously a completely different calculation that's occurring. And when you sum them up and you get that dot product, your resulting matrix will be completely different from AB. So BA is going to be very different from our AB. I'm hoping that's, intuitive, but we can do this product actually. Let me erase this. So yeah, let's rewrite our original matrix. I think it was like a 3x2 where you have 7, 8, 9, 10, 11, 11, 12, and then this will be multiplied by this 1, 2, 3, 4, 5, 6, 2x3 matrix. So let's look back at our ith row and jth column. We have our ith row, I equals 1, and our jth column, j equals 1. And the maximum value of I is going to be 3, right? We have 3 rows in that first one, and we have j equals 2, j equals 3. So there is a Cj where we should have a C3, 3, which means that our matrix is going to be a square matrix of order 3, not of order 2, like it was in A times B. So if this is B times A times B will be completely different. So let's do the ith row, 7 and 8, times the jth column, 1 and 4. So 7 times 1 plus 8 times 4, that's 7 plus 32, 39. So we're going to have A1 and C11 is going to be 39. Then let's do the ith row and the jth column for I equals 1 and j equals 2. And so that's going to be 7 and 8 times 2 and 5. So 7 times 2 plus 8 times 5. Again, this is I equals 1, j equals 2. So this will be this term. 14 plus 40 is going to be 54. So 54 is our C 1, 2. And then let's do our last term in the I equals 1 column. That's going to be the ith column 1 and the jth column 3. So that's going to be 7 times 3 and 8 times 6. I'm hoping that you can start to see this pattern that we're going to have to do for all of these. 7 times 3 and 8 times 6. This is going to be 21, 48, 69, and then that's it. We can't go any further than j equals 4 because matrix A only has 3 columns. J, the maximum value of j is going to be 3. And then we have the ith row of 2, so I equals 2, and the jth column of 1, so 1 and 4. So we're going to have to do 9 times 1 and 10 times 4. I'm hoping that this garbage truck is not too loud. I mean, I'm trying to speak slightly louder than it, but, it is a garbage truck. So we're going to have to do the ith column of, like, where I equals 2. So it starts at 9, goes to 10, and the jth column of 1. So 9 times 1 plus 10 times 4. This is 9 plus 40, 49. And then we have the ith column of 2 again, and the jth column of 2. So 9 times 2 plus 10 times 5. That's going to be 18 plus 50, 68. And then we have, again, the ith column of 2, 9 and 10. And then the jth column of 3, so 3 and 6. So 9 times 3 plus 10 times 6. We have 27, 60, 87. It's not 68, 87. And then we have our last little row. We have I equals 3 and j equals 1. So we have the ith row 11 times 1 plus 12 times 4. So we have 11 plus 48. That's going to be 59. And then we have, wait, is there some kind of, interesting. Well, anyways, let me finish this. We have I equals 3, and then j equals 2, so we have the ith column of 3 times the jth column of 2, so 11 times 2 plus 12 times 5. That's going to be 22 plus 60, 82. And then we have the ith column of 3 times the jth column of 3 lastly, so we have 11 times 3 plus 12 times 6. So that's going to be 62 or 72 plus 33. That's going to be 105. And the reason I said O is because I saw that these are adding up by 18, these are adding up by 14, and this is adding up by 10. So it's like 10, 14, 18, and then like, some kind of a 15 is increasing here, 19 is increasing here, and, wait, what? And then the pattern just kind of stops, and then it goes, oh, no, never mind. It goes 23, 23. Yeah, and so the changes between C, I1, C11, C12, and C13, that's going to be 15. C21, C22, C23, that's going to be 19. And then C31, C32, C33, that's going to be 23. So it's like incrementing by 4 along these. And this is incrementing by 4 as well, which, I mean, I think that's just a cool coincidence. It's not actually anything. Might have something to do with the fact that we are, incrementing by 1 in all of these. And this is 3 by 2 and 2 by 3, maybe some 2 by 2 magic happens, but, it's not going to fall into a similar pattern for, I would say, most other matrices, unless you have some pattern within the matrices themselves. But yeah, the AB, A times B, that matrix was a 2 by 2 matrix with completely different values, and this BA, this 3 by 2 times 2 by 3 is a 3 by 3 matrix with also completely different values. AB does not equal BA, so matrix multiplication is non-commutative. You cannot do the same things that you do with algebra to them. But that's actually why we can't do division. If AB does not equal BA, then you can't really divide by A. It won't really work. But we can do something interesting, in my opinion. That's called the inverse. We will talk about transpose in a second, even though that's not really, it's kind of math, but it's not super important for actual operations on matrices. So let's talk about inverses of matrices. This is where we're going to have to reintroduce our idea of the identity matrix, with that main diagonal of 1 and every other element being 0. So a inverse should be something like A times A inverse, we'll write that as A negative 1, should just be I. It's kind of like saying that A times 1 over A equals 1. but we're working with matrices instead of normal algebra. But division, or 1 over a, is the inverse of multiplication. So inverse of multiplication, even though we can't technically divide like we can do with multiplication, we can do the inverse. We can try and find a minus a. We can do a inverse by doing some funky stuff with the identity matrix. Even though we can't divide as we normally can, we can do this operation to get the identity matrix. And again, it's going to be like a divided by a equals 1, even though we're not technically doing division. So let's try and find the inverse of one of these matrices. In order to solve for the inverse, we have to do this following formula. It is the inverse is equal to 1 over the determinant of a, remember that, determinant times the adjugate of a, also something important. And we will talk about both of these, but the determinant of a 2 by 2 matrix and the adjugate of a 2 by 2 matrix is much easier to find than a 3 by 3 matrix, and definitely far, far easier than trying to do this of a 4 by 4 matrix. So I'm going to focus most of my time on explaining how the determinant is found for a 2 by 2 and the adjugate is found for a 2 by 2, but I will link down a genuinely beautiful representation of how you can find, or what the determinant means in terms of a 3 by 3 matrix, but the determinant of a 2 by 2 matrix I think I can explain on my own. And we will also attempt to do this A inverse of a 3 by 3 matrix, even though that will take quite a bit of time. And we can also talk about the determinant, but while I would like to explain what the determinant is, I do not have the prowess to handle drawing or trying to visually represent what the determinant of a 3 by 3 matrix would even look like. So I'm just going to stay strictly within what we've been talking about. And now, let's go into what the determinant of a 2 by 2 matrix is. So let's come up with a 2 by 2 matrix. We'll call it A, B, and C, D. Now this is, you could either think of this as 2 separate column vectors or 2 separate row vectors. We will have to think of these as row vectors because this is how the formal definition kind of looks. This is going to be AD minus BC. And we're going to have to think of these as row vectors. I know we've been working solely with column vectors up until this point, but this is going to be 2 row vectors. We have AI plus BJ, so it travels some a number of units in the x direction. A plus C, B, and then A, B. Oh, whoops. Maybe I should have edited that out. But, I mean, we know what this one is, right? This is going to be C because we had to find that for this triangle. And we also know that this has to be, well, if this point is A plus C, B, then this point's A plus C, 0. So this is going to be B. So we have to subtract not 1/2 BC, just all of BC. And then, yeah, because this is a rectangle, not a square. That's why I was getting tripped up. But let's draw some rectangles and triangles over here. This will be the same, right? This side length is D, and this side length is C, so that side length is C. And then from here, we have that this is 0, B plus D, and then we have that this is a b plus d, right? So when we have a b plus d and 0 b plus d, we know that this, oh, not c, it's going to be, we already know what that one is. We have 0 b plus d over here, and then we have, right here, we have 0 d, so the distance between these two is b. So we have another bc, and then we know that this point is going to be c b plus d, c b plus d. This point is still a plus c b plus d. So the distance between c and a plus c is going to be c, right? And or wait, no, this distance is going to be a. We started at c. Let me write down what I'm saying so that I don't get tripped up. This is cb plus d, and this is a plus c b plus d. So this distance has to be a, right? And then this distance has to be c. We have a plus c b plus d, and we have, well, I mean, we actually don't even need to calculate this. We know that this is b from there, because this is a rectangle. So we have minus 1/2 AB minus 1/2 CD and also forgot we did have another BC. We had two BCs down here, and so let me erase all of this real quick. After all of this, we have AB plus CB, or BC plus, I can factor correctly, plus, we have A plus C times B, and A plus C times D. So we have AD and DC. AD and BC, and CD. And then we subtracted minus 1/2 AB minus 1/2 AB, so minus AB. So this is no longer part of this. And then minus 1/2 CD minus 1/2 CD, so DC is no longer part of this. And then we had two BCs minus two BCs. So BC minus 2 BC is going to be negative BC, and we're left with an AD. So, yep. The determinant of a 2x2 matrix is just going to be the, well, the representation of the area of the parallelogram of two composite vectors that can be made from that 2x2 matrix. This can be written as a, like, two column vectors, because, I mean, you look back at A, B, C, D to get AI and BJ, and then C, I, and DJ. But, I mean, if you just write this as two column vectors, if you say that this is A, B, and C, D, well, if you just kind of swap these two, and you try and draw this as two column vectors, you're still going to have this minus this, right? So you could write this as A, B, C, D, but most of the time you are going to see it across A, B, and C, D. So if you just think of these two rows as two individual vectors, and you just try to find the area of the parallelogram that's created by those two vectors. And yeah, that's what the determinant is going to be. And then the adjugate of a 2x2 matrix is going to be nice and simple. It's just going to be, well, let me actually show it. Now, what is the adjugate? This is going to sound complicated, and I guess it is a little bit complicated, but for 2x2 matrices, it's actually not too difficult. The adjugate is the transpose, which I did mention very briefly beforehand, transpose of the cofactor matrix. Now, what do any of those words mean. We know what a matrix means, but what's a transpose and what's a cofactor? So a way to think of transpose is just like it's when you flip a matrix across its diagonal. So if you had a 2 by 3, well, let's do 2 by 2 really quickly so that it's a little bit easier to see. And then we had this 1, 2, 3, 4. What's its main diagonal? It's going to be A1, 1, and B, and A2, 2, so 1 and 4. And you just flip across that. So this transpose is going to be 1, 2, 3, 4. That's the transpose of this matrix. And now you might be thinking, how do we do a transpose of a matrix that is not a square matrix? So let's do a 3 by 2 matrix. We have a 1, 2, 3, 4, 5, 6. Let's let this be our 3 by 2. Now, what's the main diagonal going to be for this one? It's kind of hard to say, but let's go back to our definition of the main diagonal when j has I equal to j, so this is a11 and this is a22, so let this be our main diagonal, and we simply flip these, and if this was a larger matrix, we would have to flip this and this. So yeah, like this is a 3 by 2, so the transpose would be a 2 by 3. So let's write our main diagonal. I'm hoping that once we actually show what this would look like, it's a little bit easier. The main diagonal stays the same, it's still on that same axis, and then you flip those 3 by 2, it's still within the brackets, but when we flip that 5 across this main diagonal, we had to go 1 and then 1. So if this is, say, A3, 1, we had to go to A1, 3. And so A1, 3 will be over here. We have 5, and then this is A3, 2, and then it has to go to A2, 3. So A2, 3 will be right there. The main diagonal is right there, 1, 4, and if this was originally, wait, did I? Oops, I forgot to flip these two. But let's rewrite this. We have 1, 4, and then 2, 3. This main diagonal is still the same, but this is what, A2, 1? We made 3, which was A2, 1 originally before we did the transpose. A2, 1 became A1, 2. 2 was A1, 2, so it became A2, 1. 1, 4, the main diagonal remains the same on any transpose, but 5 went from A3, 2 to A2, 3, and 6 went from A3, 1 to, 5 went from A3, 1 to A1, 3, and then 6 went from A3, 2 to A2, 3. So yeah, you just keep the main diagonal the same, and then switch the I and j's for any ij, aij. And that's the transpose of any matrix. I'm pretty sure there might be some, really obscure examples where that doesn't work. But let's talk about the cofactor. And this is a little bit odd. Well, let's just kind of try and define it. It's kind of hard to define a cofactor. I'll just kind of say, we will, for us, I think that the best way to think of it is to just kind of... So a cofactor is the determinant of the minor. So let's write the minor, what the minor is. That's just the number that's left, or the matrix, a smaller matrix that's left. Matrix is probably the best word, because matrices can also be one number, which is what we're going to have for our 2 by 2. A minor is just the matrix that's left after eliminating the row and column that some element aij has. So for some I or j, you just calculate the minor by seeing the matrix that's left after you eliminate the row and column that aij falls upon. So let's just draw a really quick matrix. We have say 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, perfect. And then let's try and find the minor of this matrix. So let's say the minor at this element 5. What are the i's and j's? Well, I is equal to 2, and then j is equal to 2. I is number of rows. Wait, does that make sense? No. I should be on this side, and j should be on this side, right? Yeah, no, I'm losing it. I equals 2, j equals 2. And so you have to eliminate every single value that are on these things, including 5. And what you're left with is this matrix 1, 3, 7, 9. So the minor at 2, 2 is equal to this matrix of 1, 3, 7, 9. And we said that the determinant of this minor is going to be called the cofactor. So let's call it C. C22 is going to be the determinant of M22. So let's go back to how we find the inverse of a 2 by 2 matrix, because this one's going to be nice and easy. We're going to have 1 over the determinant times the adjugate transpose. I mean, not the adjugate transpose, the adjugate of the matrix. So 1 over determinant A times adjugate A. That should not be uppercase A. Adjugate A. There we go. And adjugate is just determinant of the minor. So, yeah, that sounds like a lot, and it is a lot, but we will look at this really quickly. Let's do adjugate A, and we are trying to find the inverse of this function. We'll have 1, 4, 2, 3, right? And so we said that we needed to do the diagonal and then flip these. So we have 1, 4, and then 3, 2. That's going to be the transpose. And then we have to do the cofactors of like the transpose, right? So, oh wait, let me do this correctly. So this is the transpose of the cofactor matrix. So we're going to have to find the transpose after this. So let's find the cofactor matrix. We have 1, 2, 3, 4. So let's find the minor for 1. We have to eliminate everything there. So M1, 1 is going to be equal to 4. And then we have to do the same thing for 2. Or M1, 2. So let's go back 1, 2, 3, 4. When we eliminate the M1, 2, so M1, 2 is 3. If we eliminate everything that's on that, we will only have 2 left. So M1, 2 is equal to 2. And then M2, 1. We have everything on this row and column. It's going to be only 3 that's left. So I'm only not crossing these out because I feel like it's going to get a little bit tedious. But we have 3 that's left, and then last one I can cross off. We have M2, 2. So everything on this column, everything on that row, we're only going to have 1 left. So the minor, like the matrix of this minor, is going to be 4, 1, and then 2, 3. Right? And then from here, we have to do something a little bit weird. The cofactor of anything, we're going to define this as, wait, did I say something wrong? No. Like, okay, this is what the cofactor is. I feel like I might have said that the cofactor was something else, but the cofactor is defined as if you have a cofactor at Cij, then this is equal to negative 1 to the power of I plus j. Let me actually attempt to write this slightly better. Oops. Let me also erase this. We have the cofactor, the cofactor of some element Cij is equal to negative 1 to the power of I plus j times the minor of uh, the minor of ij. So yeah, this is a very, I wouldn't say it's a simple formula to remember, but this is definitely a very difficult formula to prove because it requires like understanding of more ideas past this to actually prove this fundamental idea. It's kind of like how you can't really prove that, you know, I don't know, like that the number of countable sets, like the the set of natural numbers is countable. You have to know more about the natural numbers beforehand before you can prove this somewhat like basic idea. So yeah, and like in that way, trying to prove why the cofactor of ij is this is a little bit too difficult for us right now. But you know, maybe in some future video I might be able to prove it, and I might even try and find a more normal proof that I could put in the comments down below, or description. Dang, not good at this whole YouTube thing. But yeah, let's do the cofactor at C11. So C11 is going to be negative 1 to the power of 1 plus 1, so 2, times M11, so 4. So we're going to have, that's a, all of this seems relatively important, but let me erase the A inverse. We're going to have negative 1 squared times 4, so 4. That's going to be C11, and then C12 is going to be, C12 is going to be negative 1 to the power of 1 plus 2 times M12, so 2. So we're going to have negative 2. And then the negative 1 to the power of 2 plus 1 for M21. It's also going to be negative 1 to the power of 3 times 3. So that's going to be negative 3. And then m to the power, negative 1 to the power of 2 plus 2, so 4. Times m22, so that's going to be 1, so that's going to be positive 1. This is the cofactor matrix of, well, the transpose of the cofactor matrix. So this is the adjugate of all of this. So it might seem somewhat difficult to really, understand, and it is kind of difficult. It's more just like knowing than understanding, which is something that I personally dislike. But I think for us right now, remember, we are at like the letters of the alphabet. We can't really talk about understanding the letters and why that is, because if you try to understand the letters of the alphabet, you'd have to know Old English and the stems of certain letters and how like they were drawn and like all sorts of stuff. But since we're only working with matrices, we can't really go past the matrices. We can't really understand the very basics of matrices because, we're just starting. And matrices are so broad as like a mathematical topic that it's kind of hard to prove certain things about them. But, it doesn't hurt us. We can still, do this. So, yeah, let's see. This is the adjugate of A, right? If this is, if A was equal to 1, 2, 3, 4, adjugate of A is equal to this. And you can actually kind of just think of the adjugate of a 2 by 2 as flipping the main diagonal and flipping the other diagonal and then adding a negative, right? Because 2 and 3, those are flipped with a negative, and then the main diagonal, 1 and 4, those are also flipped. That's what the adjugate A is written as. You might even see this like formula. It's adjugate A. If A is a 2 by 2, it's going to be written as, well, if we have A equals A, B, C, D. Then adjugate A is going to be D, negative B, negative C, and then positive A. So you just flip the main diagonal, you flip the other diagonal, and you add negatives. So that's the adjugate of A. Now we need to do the determinant of A, which we did talk about for quite a little bit. It's the parallelogram, the area of the parallelogram that you create when you have two vectors. And the area of that parallelogram, and of this one, we have 1, 2, 3, 4. So AD is 1 times 4 minus BC. So 2 times 3, AD minus BC, that's going to be 4 minus 6. So we have negative 2. And then we have 1 over determinant A times the adjugate of A. So we have negative 1 half times 4, negative 3, negative 2, positive 1. And as we did with these scalars, we can just multiply this k to every single one of these. So we have negative 1 half times 4 is going to be negative 2. And then you have positive 3 halves, 1, and then negative 1 half. That's going to be the inverse of this. And we can actually try and calculate this to make sure that we're correct. Let's find a good place to erase. Oh, wait, I forgot something really important. The adjugate is the transpose of the cofactor matrix, right? And we found the cofactor matrix. This is not the adjugate. I'm sorry. It's not embarrassing because, everybody gets something wrong at some point. But, yeah, I hope I didn't confuse anybody. This is the cofactor matrix, right? We did the cofactors. We did negative 1 to the power of I plus j times the minor of every single element. And we have to do the transpose now. So transpose, again, we have to keep the diagonal the same. It's going to be 4 and 1. And then we have to flip every other element. So this is going to be 4 and negative 2, negative 3. The actual formula is if you have some matrix A, B, C, D, the one that I showed you, when you flip these and then add negatives, so negative B, negative C, that would be the cofactor matrix of a like matrix that looks like this, but the actual adjugate is going to be written as dA and negative B, negative C. So these, this diagonal actually stays the same, and you add negatives to it. Because in the cofactor matrix, we had to flip them, and then with the transpose, we have to actually flip them again. So we essentially keep everything the same. And from here, now we get the actual correct multiplication. So I'm sorry about that. Yeah, no, that's not great. 1 times 4 minus 3 times 2 is still negative 2, so we have 1 half, negative 1 half, and then times the 4, negative 2, negative 3, and then 1. Yeah, this should be correct. We have negative 2, top left, positive 1, 3 halves, and then 1. Or negative 1 half. Excuse me. Alright, now we can actually prove, or not really prove, but just see that the inverse of a matrix is going to be the identity function, or the identity matrix. So if this is the inverse of that, when we do a multiplication of the two, we should get the identity. So we have 1, 2, 3, 4 times negative 2, 1, 3 halves, negative 1 half. Alright, so let's do that. We have the ith row is going to be, it's going to be I equals 1 and I equals 3, and then j equals 1 and j equals 1. So we're going to have 1 times negative 2 for this C11. 1 times negative 2 plus 3 times 1. and maybe I shouldn't put that like a dash. I'll just put a line. 1, 3, and then for C 1, 2, we're going to have the ith row be 1, and then the jth row be 2. So we have 1 times 3 halves minus, plus 3 times negative 1 half. So minus 3 times 1 half. And then bracket should go all the way down. We have the element C2, 1, so we're going to have to do the ith row being 2, and then the jth column being 1. So we have 2 times negative 2 plus 4 times 1. And then from here, we have the last one, that being the ith row equals 2, and then the jth row equals 2 as well. So we have 2 times 3 halves minus 4 times 1 half. All right. Then from here, we can kind of solve this in our head. We have negative 2 plus 3 is going to be 1, and then 3 halves minus 3 half is going to be 0. Negative 4 plus 4 is going to be 0, and then 3 minus 4 is going to be, wait, what? Oh, wait. Yeah, no, I was thinking 3 minus 4, but it's actually 4 times 1 half, so it's going to be 3 minus 2, which is equal to 1. All right, perfect. And this is the identity matrix, right? This is the main diagonal is all 1s, and every other element is 0 of some square matrix. So, yeah, I mean, we can kind of see that the identity matrix is going to be just left inverse, and not left inverse, thinking in terms of set theory, regular inverse and actual function. So it's not actually division, but it is the inverse of multiplication. So, you can kind of think of it as division in your head. And now let's try and do, well, let's just review what we went over, because I feel like I might have confused a couple people, because, I mean, I wasn't making too much sense, but Cij, or the cofactor at some element of this larger cofactor matrix, is going to be equal to negative 1 to the power of I plus j times m1, mij. And the mij is the minor. So in order to find the minor, we had to do the blocking thing. When we have some like matrix of A1, 1, A1, 2, on and on, A2, 1, A2, 2, on and on, A3, 1, on and across that diagonal also increase. For this one, you have to take some ij, so if it was aij where a or I equals 2 and j equals 2, you have to block out every other value with I equals 2 and every other value with j equals 2. And then you have this matrix of whatever's left after all of that, and then you have to calculate the determinant. Yeah, you just have to calculate it. You have to, you have to calculate okay, I can speak English. I know I can. You have to calculate the determinant of the minor and then multiply it by, what am I saying? Okay. I can speak English, I promise. You have, once you've eliminated the row and column that a certain element of A, big A, and you have, you've eliminated the row and column that element lies upon, you have a matrix that's left over. And the determinant of that matrix is called the minor at that element's row and column. And once you've calculated the determinant of the matrix that's left after you blocked both those rows and columns, then you have to multiply it by negative 1 to the power of I plus j, or the position of that element, and then you get the cofactor. Once you have the cofactor matrix for every value of I and j that you can, you have to do cofactor transpose, or adjunct A, or adjugate A. Adjunct is, I think it's still considered a term that you can use for this, but it has applications that are past just the adjugate. So You have adjugate A is equal to the transpose of the cofactor matrix, and then you have to divide the cofactor transpose, or the adjugate, by the determinant of A. And I said that I was going to do a 3x3 matrix, but I think it's probably better to just kind of look at one and see how we would do that. So let's write a basic A11, A12, A13, A21, A22, A23, A31, A32, and then A33. Alright, that's going to be our 3x3, and it's the basic one. And we have to find the minor of every single element, so let's block out the row and column that A11 lies upon, and we're going to be left with this matrix. We're going to have A22, A23, A32, and A33. And we have to calculate the determinant of that. And then we just keep that in our back memory. And once we've calculated the determinant of this part, we do need to multiply it by -1 to the power of 1 plus 1. So it'll just be the positive determinant of that. And let's see, yep, we have A12. We have to multiply, we have to find the minor first, so we block out the row and column, so we're going to be left with this, 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 this. And then we find the determinant of that matrix. So this matrix will be like A21, A31, A23, and A33. This is a 2x2 matrix. There isn't like a blank column in between. So once you find the determinant of that, you have to multiply it by -1 to the power of 1 plus 2. So -1 is what you're going to have after you do it to the power of 3. And that's multiplied by the determinant at that point. And then we do the same thing for A13. We block out the row and column. We're left with this. We do the determinant. We multiply it by -1 to the power of 1 plus 3. And then you just have to do that for every single term. You block out row and column like this, and you have A12, A13, A32, A33. Find the determinant, do it to the power, multiply it by -1 to the power of 2 plus 1. A22, same thing. A23, A31. You have to do that individually for each and every part. And the minor is just the determinant of that 2x2 matrix that's left. And you actually might have seen something like this. So if we know that these even powers of -1 will be positive, you might just see this be how you remember. It's just oscillating between positive, negative, and yeah. This makes sense because, this is A11, 1 plus 1 is 2, even, so -1 to the power of 2 is going to be 1, positive. And then negative because this is A12, so, a 1 plus 2 is 3, which is odd. -1 to the power of 3 is going to be negative. And then A13, so this is going to be, 1 plus 3, 4, and on and on. You will have this this plus minus kind of oscillating pattern between these two, and you can think of it like that. I think it's probably at least a little bit more beneficial to remember like this, because if you forget this, it's not super easy to forget, but if you do forget this pattern, I think it's definitely helpful to remember what the cofactor is even supposed to be. And then from here, you have to find the transpose of the cofactor matrix, because all you've been doing is finding Cij for every C11, C22, C33, C12, C, and on and on for that 3x3. But now you need to actually do the transpose, and the transpose is called the adjugate. So adjugate A is equal to the transpose of the cofactor matrix, what we wrote down there, so CT. And then all of that needs to be multiplied by 1 over the determinant. 1 over determinant A. So yeah, that's a lot. I know that's a lot, especially for a 3x3 matrix. It will get very, messy very quickly. But once you understand that, all you need to do is find the minor, so block out the row and column that like element lies upon, and then do the determinant of the matrix that's left, and then multiply it by -1 to the power of that like element's position, and then you just do the transpose of whatever like matrix you have at the end of all of those minors, and then you do the determinant of A. Let's actually talk about the determinant of a 3 by 3 really quickly. So let's not sure how I should write this. This one I'm just going to write down because like I mean I will put a video down below of like this just honestly very well done demonstration of why this is the way it is. You kind of have to think of well, we said that 1 by 2 or that like that kind of column vector is two-dimensional, right? And then when you add another dimensional and you have another value, 1, 2, 3, you have a three-dimensional thing. So when you're working with a 2 by 2 or a square, you're going to be working with a parallelogram, as we kind of demonstrated. But when you're working with a 3 by 3, you're working with like the prism version of a parallelogram. You're going to be working with a 3D object. So there's a lot more to calculate when you're trying to find the like when you're trying to find the diagonal across that object. So let's just kind of I'm just going to write down what the determinant of a 3 by 3 matrix is. So if you have A is equal to A, B, C, and then D, E, F, G, H, I, the determinant is going to be A times EI minus FH minus B times DI minus FG. Well, let me actually give myself more space. Okay, let's write this one more time. We have A times EI minus FH minus B times DIFG plus C DH minus EG. Again, I will show, or not show, I will just put down in the comments. Why do I keep saying comments? I know it's description. I'll put down something in the comments of, how this is like seen and how you can represent this, but honestly, it's most likely going to be better for you if you just memorize this, which is something that I would almost never say. But, you can also think of this as the formula of, so this is kind of like the minor. So the determinant is going to be, EI minus FH. That's going to be EI minus FH. So if you just do the minor of A, you're going to have this EFHI. So if you do the determinant of the minor of A times A, and then you do the, if you do the determinant of B, so let's do the minor of B, you have this and this, so you're left with D, G, F, I, so D, I, and F, G. You're going to be left with the determinant of the minor, so, wait, it's not the determinant of the minor, what am I saying? No, it's just the minor, because the minor is already a determinant, but, it's going to be just A times MA minus B MB plus C MC. That's just kind of the pattern that you might need to remember, but there is a very nice looking proof that does require like actual artistic ability, but yeah, that's the determinant of a 3 by 3, and so once you've calculated that, you do 1 over that determinant times the adjugate of A, which we just talked about. And yeah, I think that's pretty much all we need to talk about. We did talk about some of the, transpose, inverses, basic operations like scalar multiplication, matrix multiplication, addition. We talked about why division is not possible. Oh, and one last thing, determinant of A cannot equal 0 whenever you're, like, you can't find an inverse of every single function, because if your determinant is equal to 0, then you can't do 1 over determinant A times adjugate A, because you can't divide by 0, right? So, yeah, your determinant cannot equal 0. But yeah, we talked about, let me gather what I'm about to say. We talked about how the inverse is just the adjugate over the determinant, and we find the adjugate by finding the minors and doing the cofactor matrix of all the minors, and then doing the transpose of that cofactor matrix. And we also talked about matrix multiplication, how you just do every term in the ith row times every term in the jth column, where like it's the same, and then you sum them up. We talked about how a matrix multiplication is non-commutative, so AB does not equal BA. We talked about how you add matrices. We talked about how you multiply matrices by scalars. And we talked about some of the connections between vectors and matrices. So, yeah, I know this video was not, particularly well organized, and I did lose my train of thought quite a few times. I am somewhat tired. But, yeah, that was just I hope a relatively okay introduction into matrices as a topic, but I won't delude myself into thinking it was particularly great. I've never been, stellar at matrices. Like, I don't know. Wait, did I not even talk about how you can think of matrices as systems of equations? Oh no. Well, well, I can do an example video relatively soon about that. Yeah, no, that's really not good. Okay, so I'm just gonna really quick go back to something that I should have just mentioned much earlier. If you think of a matrix as just an arrangement of numbers, you can actually just think of this row. So say you have 3, 4, and then 7, 6. And we said that if you think of this row as a vector and this is a vector, then you have 3i plus 4j and 7i plus 6j. And if you have some this is a systems of equations, right? If we said that I is a unit vector in the x direction and j is a unit vector in the y direction, so we can write this as 3x plus 4y and 7x plus 6y, and this can be used as a representation of a systems of equations, and you can do some calculations. I definitely do need to talk about that at some point. Yeah, the fact that I didn't even mention it does not bode particularly well for anybody understanding what I'm saying, or even me understanding what I'm saying if I try to edit any of this. But yeah, not the greatest video. In fact, probably one of the worst videos that I've made so far. But it's just it's there. And let's end off with an album recommendation. What have I been listening to? I've been listening to quite a bit. Let me see. I did talk about Reggie's song that came out a little bit ago, and it was fantastic. I haven't stopped listening to it, but I thought that King's Disease 2, I listened to King's Disease 2 a little while ago too, so King's Disease 2 by Nas. I don't know how this man is still coming out with actual music that's good, like he's old, very much so, and not in a disrespectful way, but more like in a have fun with the rest of your life and don't care about rap anymore kind of way. But he just sounds so hungry, and this production by Hit Boy, it's amazing, I don't think there's a particularly bad beat. Maybe there's some production choices that don't have the greatest impact to them or anything, but just far and away, it's one of the best albums that Nas has ever come out with, other than like Illmatic and Stillmatic. But like, I don't know, man. It's just like, because some of the earlier stuff that Nas has dropped outside of his like original classic run. I mean, it wasn't bad or anything, but it was definitely bland. It was definitely more of the same, and Nas just sounds so much more alive now than he did in like 2006. So it's kind of crazy to think that he just has this like late stage um, masterpiece, at least for his standards. And yeah, it's pretty crazy. All the bars are pretty, you know, creative to say the least, but it's definitely a very enjoyable listen. And if you do want to listen to this album, please comment down below. And if you like this video, please comment down below. If you did not like this video, which I mean, I wouldn't blame you. This wasn't the greatest video. In fact, this is probably the worst video that I've made so far. But if you didn't like this video, please comment down below. Constructive criticism is always encouraged, and if you're not in the mood for constructive criticism or a comment, then I swear to God, I haven't exercised in a while. I've just been doing work, but you know, do some lateral side planks. Yeah. Okay. Bye.